Okay, we're going to try something a little different here. I'm trying to record this from my iPad, so we'll see if it works. Okay, so what we need to talk about today is section 15.6. And the first concept that's in there is this concept of a reaction quotient, which is Q. So this is a little complicated, the difference between Q and K. And the way that this works, basically, Q is like K, except it's the same expression, but it's when the system is not at equilibrium. Okay, so you can envision maybe a reaction here. The reaction we've been using a lot is the N2O4 in equilibrium with the 2NO2. Okay, so if you envision that reaction happening, and maybe we start the reaction by just adding N2O4. So at the very beginning, there is no NO2, right? So at first, this reaction is going to proceed only in this direction. That's the only way that it can go, all right? Eventually, once there's some NO2 that starts changing back to the N2O4, then it will start going back in the other direction as well, okay? So the idea here is that we have this Q value that will tell us which direction the equation needs to go, or the reaction needs to go, in order to reach equilibrium. Okay? So again, based on my example here, at the beginning this reaction would need to go towards the products in order to get to equilibrium in the first place, because there's only N2O4 to start with. So what we can do basically is calculate Q, and if we calculate Q and then compare it to a known K value, a known equilibrium constant, we can figure out which direction the reaction needs to go in order to get to K. So you're using, for Q, you're using initial concentrations instead of equilibrium concentrations. Alright, so you just have to kind of keep that in mind. What we're using here is initial instead of equilibrium when we're calculating Q. Q equals K at equilibrium, okay? If Q is less than K, then the forward reaction has to occur to get to equilibrium. If Q is greater than K, then the reverse reaction has to occur. And I'll show you an example of this in a second, and I think it'll make sense, okay? So if Q is greater than K, then Q will decrease until it equals KEQ. What they didn't put up here is that the Q would have to increase on this one. Sorry. Trying to write with my finger. It's taking a little getting used to. Alright. So, again, this is just in graphical form showing what we basically just said. Okay. If the Q is less than K, well, okay, if the Q is equal to K, then we're at equilibrium. That's the one that's highlighted right now. If the Q is greater than K, then the equilibrium will shift back to the left. It's going to form more reactants until the Q and the K are equal to one another, and then if the Q is less than K, then the reaction will need to form some products, some additional products, until it reaches equilibrium. Okay? So here's an example of a type of exercise that you might have with this. So you've got, at 448 degrees, the equilibrium constant for the reaction H2 plus I2 plus, or yields 2HI, is 51. So they're giving you your K. But then what they give you down here, they give you initial concentrations. So they're giving you 2 times 10 to the negative second moles of HI, 1 times 10 to the negative second moles of H2, and 3 times 10 to the negative second moles of I2. And this is in a 2-liter container, so that's a little bit nasty. We just have to be careful here to make sure that when we actually plug these values in for Q, that we're using concentrations rather than using the number of moles. So they give you the number of moles, they give you the fact that it's in a 2-liter container, so you're going to have to divide by 2 in order to get to your concentration. Alright? So then what we're going to do here is we're basically going to find Q. Alright? Because what we're given here is initial concentrations. Start with is our key there that shows us these are initial concentrations. So what we're going to do, we're going to solve for Q over here, okay, and our Q expression, if we come back over here, it's just like our equilibrium expression, so products over reactants, so we'll have the concentration of HI squared divided by the concentration of the H2 times the concentration of the I2. Okay, so that's our Q expression. Again, it's just like the equilibrium expression, except we're plugging in initial concentrations instead. So when we plug in those numbers that they gave us, and again, I'm dividing everything by 2 to get concentration instead of number of moles. So I have 2 times 10 to the negative second moles of HI, which would give me 1 times 10 to the negative second molar here. But again, once we plug it into the expression, they become activities, so they don't have units. Okay? And then we've got, let's see, 1 times 10 to the negative second moles of H2, which becomes 0.5 times 10 to the negative second, which is 5 times 10 to the negative third for the H2. And then we've got, sorry, my furnace just kicked on. Then we've got 3 times 10 to the negative second moles of I2. So that's going to be 1.5 times 10 to the negative second. We plug that in. So then if we solve for that, they've already given us the answer over here. Okay, they told us the Q equals 1.3. Alright, so now we have to figure out what that means, what that's telling us. Alright, so they told us that our K is equal to 51. If our Q is equal to 1.3, that's obviously a lot lower than our equilibrium value. Okay, so again, just thinking about what this means. This needs to get bigger, essentially, okay, in order to reach equilibrium. Well, the way we're going to get it, make it bigger, is if the HI concentration increases and the H2 and I2 concentration decrease. Alright, so you can kind of think about it in those terms. That's going to make our Q bigger, which is going to cause it to approach K until eventually Q equals K. Alright, so then we come back over here and look. HI, again, is our product, so the reaction is going to need to shift in this direction until it gets to equilibrium. In other words, we need to make more HI before we can reach equilibrium with this equation, okay, or with this reaction. So that's what it's basically telling us. Based on our starting amounts, it's telling us which direction the equilibrium is going to move to get us to the right concentration. So, let's see, where do I have space to do this? I may have to erase all of this. Let's see how good the eraser is here. Not very good. It doesn't give me an option to... see, I'm still learning this process here. There's got to be a way to clear this slide. But I'll just get rid of some of the stuff down at the bottom here so that I can show you a graph. Okay, so remember those graphs that you saw at the very beginning of the unit where the concentration of one thing is going up while the concentration of the other things were going down? So in this example, for us to reach equilibrium, the HI concentration, it's not going to start out at 0 because we did have some HI to begin with, okay? But that's going to need to increase until it eventually levels off, okay? The H2 and the I2 concentrations are going to need to decrease. Now, I'm not exactly sure. We'd have to do an additional calculation here to figure out exactly what those final concentrations would be, okay? But your H2 and your I2, let's see, let me try and get this right. The H2 actually starts lower, so this is our HI here. Our H2 actually starts lower in concentration than the HI, but it decreases even a little bit more. Okay, so that's your H2, and then our I2 here starts out at 3 times 10 to the negative second, so that starts out with a higher amount than any of the others, but it is going to decrease as well. Okay, and again, I don't know if the ending concentrations here are exactly right, but that gives you sort of a graphical picture of what's happening in this reaction in order for it to reach equilibrium. The reactant concentrations have to decrease while the product concentration increases. Okay. this next one is very similar to that, except it's giving you a different scenario where this time the Q is actually, once you work it out, the Q ends up being greater than K. It tells you the value for K is 0.338, and then once you calculate the value for Q here, you're going to get 16. Okay? So when the Q is greater than K, now again, just to make sure we've got this, if I write my Q expression for this one, products over reactants, and this time we're doing it in terms of pressures, we're doing the Kp. Alright, so I've got my SO2, my pressure of SO2, and that's going to be squared because it's a coefficient 2. That's a bad 2, sorry. And then I've got my O2, so times my pressure of my O2, these are both the products here, over my reactant, which is the SO3, so pressure of the SO3, and that's also squared. So there's my Q expression, okay? So basically what I have to do is think about if I want my Q to be smaller, okay? Because in this example, again, Q is bigger than K at this point, so it needs to get smaller in order to reach equilibrium. Well, that means really the concentration of my reactant needs to increase in order to make the Q value smaller than it is right now. And then the concentration of my products need to decrease. Okay, so that tells me this particular reaction is going to shift in this direction, towards the reactants. Alright, so again, if I was drawing a graph here, I've got the pressure of my SO3 starting out at 0.16 atmospheres. That's going to need to increase. Okay, so the pressure of my SO3 starting out at 0.16 is going to go up. Sorry, that was supposed to level off. The SO2, 0.41 atmospheres, so it starts a little bit higher, but it's going to decrease over time. Okay, and then the pressure of my O2 is 2.5, and that starts out quite a bit higher than the others. Okay, so it's up here, but then it decreases over time too. And again, I don't know if it ends up lower than the SO3 or not. We'd have to do a separate calculation there. But that's basically what's happening graphically to the concentrations of these things. I guess I should say this is the concentration over time or reaction progress, however you want to say that. Okay, so that's the idea with Q versus K. Hopefully that makes sense. Okay, so here's another example. Now, you may notice we're just going to talk about some additional equilibrium calculations that you can do here. Okay, so you can forget about Q for a minute. We're just talking about various calculations. Now, all the calculations we've done so far with K have involved us finding the equilibrium constant. Alright, now we're going to do some calculations where you're actually given the equilibrium constant. You have to figure out one of the equilibrium concentrations or equilibrium partial pressures. Okay, so this is an example of that. It's giving you K already. K is given to you right there. And they're giving you the equilibrium partial pressure of two of the gases in the reaction, and then they want the partial pressure of the other one. Alright, so it shouldn't be too hard to figure out. This is just a basic algebra thing here. Alright, so our K expression for this one is going to be let's see, NH3, pressure of the NH3 squared divided by pressure of our N2 times the pressure of our H2 cubed. Okay, so that's our basic expression there. What we have this time, we already have our K value, so we can plug that into the equation. 1.45 times 10 to the negative fifth is equal to the pressure of the NH3. That's what we don't know at this point. That's what they're asking us for, so I'm just going to call that X. Now X is squared because of the expression. Pressure of our H2 is 0.928. Okay, and then the pressure of our, whoops, sorry, my fault. Okay, so the pressure of our N2 is what we're starting with here. Pressure of our N2 is 0.432. And then the pressure of our H2 is 0.928, and that needs to be cubed. Okay? So then what you're ultimately going to end up doing here is you're going to need to multiply, just show this one to you. I think you guys can probably figure this out, but, you know, just in case. If you take 0.432 and you multiply that by the 0.928 to the third, you should get 0.345 or something like that. And then if you take that whole expression and multiply it by the 1.45 times 10 to the negative fifth, okay? Sorry, I'm having trouble with my calculator here. When you multiply that together, you know what, I can just look this one up. You should end up with 5.01 times 10 to the negative sixth is equal to x squared. So then to solve for both sides, you just, you know, take the square root of both sides. I think you guys could have figured out the math on that. Once you solve for x, obviously in math class, when you have an x squared, you get two values, a positive and a negative. We're just going to use the positive. The negative doesn't make any sense in this context. We wouldn't want a negative pressure. Okay, so you use that value that you get. Your x value there should be 2.24 times 10 to the negative third. Okay, so that should be your value for NH3. Alright, so hopefully that makes sense. It's not too difficult. Where it gets a little tough, and this is just another example that's very similar to the last one, so we'll skip over that. Where it gets tough here, let me skip over some of these, is when we have something like this. Okay, so an example here, we basically have two initial concentrations given to us, okay, and it's not stated as concentration, but we have a 1 liter flask and there's 1 mole and 2 moles, so that's going to equal the concentration since we're in a 1 liter flask. But that's all they're giving us, and then they're giving us the value of Kc, and that's it. So this one's a little tricky. They want the partial pressures of H2, I2, and HI at equilibrium. Okay? And we don't know any of the equilibrium concentrations at this point. Now what we did in the last section, we were given an initial concentration and a final concentration for at least one of them so that we could figure out the change if we did an ice table. Well, we're going to do an ice table here, but this ice table is going to be a little bit different, okay? This ice table, we already have the K value, so we're actually solving for something a little different. So my reaction here, again, is H2 plus I2 yields 2HI. It's a nice, easy reaction to do this for. And then I'm going to make my ICE here. And I may have to erase some of this at some point because I'm going to run out of room. But what we know at this point, we've got 1.000 molar H2. Okay, and we have 2.000 molar of I2. And we know, just based on the way that it's said here, said the flask is filled with 1 molar H2, 1 molar or 2 molar I2. So we can assume that there's none of the HI to begin with here. So we can assume that that's 0 to start out with. Okay? So here's the tricky part. We don't know how this thing changed. Okay, but we do know based on the stoichiometry how they're going to change relative to one another. So let's say that I say my H decreases by minus X. Now I know it's going to decrease because I only have reactants right now, So the only direction this thing can really go is towards the product at this point. Okay? The reactant concentrations are going to decrease. The product concentration is going to increase. Alright? Otherwise there's no reaction here. So I know that my H2 is going to go down by X, whatever X is. Well, just based on the stoichiometry, that means my I2 is also going to go down by X because it's a 1-to-1 stoichiometry between them. That means that my HI is going to increase by 2x because there's a coefficient 2 in front of the HI. Alright? So now I can kind of write this as, and I'm going to simplify my sig figs here and then we'll watch those again at the end. This will be 1 minus x. This will be 2 minus x. Sorry, that's supposed to be a minus. That looks like an equal sign. And then this is just 2x. Okay? So then I can plug this into my equilibrium expression, and again, we know the value for K. It's given to us right here, 50.5. So 50.5 is equal to, and if I write this equilibrium expression, my HI, I'm going to try and do this without, well here, I can back up a little bit and I can show you the equilibrium expression for that one. No, I can't because I erased it. Of course. The HI is on top of the equation and it's squared. Okay? So I need to square my 2x value right here. The whole thing. And that's going to be divided by 1 minus x times 2 minus x. Well, this is obviously getting a little bit messy already. So what we have to do here is quite a bit of algebra. You're going to end up with an x squared term. When you factor this part down here, you're going to end up with just an x term, and then you're going to end up with some numbers. So eventually, what that's going to give you is a quadratic. Okay, you're going to have a quadratic equation. What you have to do then is you have to use the quadratic formula to solve for that equation. Alright? Now, they take you through how to do this in the book. The formula for the quadratic equation is on page, I think it's 1108 in your book. Okay? So what you have to do here basically is FOIL this bottom part. Hopefully you guys know what I mean by FOIL. First, multiply the first terms together, then multiply the outer terms together, then multiply the inner terms together, and then multiply the last terms together. Okay? Once you've done all of that, then you can multiply the 50.5 by that entire bottom section. Okay? And then you've got your 4x squared over on the other side. Okay? So we're just solving for this thing. And again, this is all in the book, so I'm not going to write all this out because I don't have a lot of room for it either. Plus, we're running out of time here. But basically, once you get your expression, it should be 46.5x squared minus 100. See, I'm not going to be able to fit all this. 151.5x plus, I'll just do it like this, 101.0 is equal to 0. Okay? And once you have your expression set up that way, so you've got your x squared, you've got your x, you've got your number, and you've got it equal to 0, then you can plug it into the quadratic formula. Okay? Plug this into the quadratic formula. You just have to remember what your a term, this is your a term right here, this is your b term, and this is your c term down here. So you just basically plug that into the quadratic formula, and that's going to solve the problem for you. Now again, you're going to get two x values here. We just ignore the one that doesn't make any sense, okay? Because for one of these, you're going to get a number that gives you a negative concentration, and that's obviously not correct. So then you want to use the one that gives you a positive concentration for everything. And that would then give you the values that you need for your equilibrium concentrations for H2, I2, and the HI. Okay? A little bit complicated. Hopefully that makes sense. You can look at the sample exercise in the book as well, just to kind of walk through the process. But that, again, just remember that is something that you only need to do if you're only given the initial concentrations and a K value, and that's it. Okay? If you're given an initial concentration and a final, then you don't have to use X for the change. You'll be able to figure out the actual number for the change, and then it's not all that difficult. So just, this one specific scenario where you would have to use the quadratic formula for it. I'm showing it to you because I think it's worthwhile for you to know. I don't think you're going to see something like that on the AP exam. Alright? So, that's it for today, I'm pretty sure. Yep. Well, next time we'll talk about Le Chatelier's principle. So, that will be it. I guess have a good snow day, and we'll see you guys tomorrow.